In today's lecture, we will discuss subsets. Let's go through the definition first. Let's say we have two sets A and B. If every element in a set A is also an element of a set B, then A is called a subset of the set B. We can also say that A is contained in B or B contains A. Symbolically, we will write the subset as A. We'll use the symbol. This is the symbol for a subset. A is a subset of B. And it can be read as A is a subset of B. Now, sometimes it can be also read as A is contained in B. Means exactly the same thing. However, most of the time I will be using the first one, that A is a subset of B. We'll come to this a little later. This means that thus A is a subset of B if we have an element X that belonging to the set A implies, so this is the symbol for implies, X also belongs to the set B. So this is what it means when we say that A is a subset of B. Now A is contained in B. We can also say, we can also represent it as B contains A. It means exactly the same thing. B contains A, but the moment we say B contains A, then we'll be writing it symbolically as B contains A. And this particular symbol will be also referred to as the superset. So we can say B is a superset of A because B contains A. And if A is not a subset of B, then symbolically we can express it as A. We'll use the symbol for subset. A is a subset for B, but since A is not a subset of B, we will cross it out. Now, this means that A is not a subset of B. Or we can say A is not contained in B. Or we can say B does not contain A. Let's try to understand this with the help of an example. So let's say we have three sets A, B, and C. Now here set A contains the elements 1, 2. Now B contains the elements 2, 1, 1. Now as you can see here, the element 1 is getting repeated. So we don't have to write it twice. We'll only consider a single element 1. Then we have the set C containing the elements 1, 2, and 3. Now let's discuss set A and set B. So we'll first look at set A and set B. Now we'll start with the element of A. So here, let's say we start with the element 1. 1 is an element of the set A, and that same element 1 is also an element of set B. Okay, so that means we are fine with the element 1. If it is present in A, it should be also present in the set B. Then we will consider the second element in A. So 2 is an element in A, and the same element 2 is also an element of the set B. So we see that the second element is also present in both the two sets. So here we can say that A is going to be a subset of B. Or in other words, we can say that A is contained in B, or we can say B contains the set A. Okay, what about the set A and C? Let's look at set A and set C. So here we see here that the element 1 is contained in the set A, and the same element 1 is also contained in the set C. Then we have the second element 2, which is contained in A, and it is also contained in the set C. Now, we can say that A is a subset of C. However, if we look at the third element, there is one more element in set C. So here 3 is an element that belongs to the set C, but 3 does not belongs to the set A. So in a way, we can think about it's like this. The cardinal number of set A, the cardinality of set A, that's 2 because it has got 2 elements, whereas the cardinality of set C, that's equals to 3. Now clearly 2 is less than 3. So here what we can say, that A is going to be a proper subset of the set C. So here we are not going to use the horizontal line. So we will say that A is a proper subset of C, to distinguish from the other definition, that's a subset. A is a proper subset of C. Right. Or it can say that here the set A is not equals to the set C. However, in the previous case, when we say that A is a subset of B, clearly we can say that A is equals to B. However, this is not a complete definition. We can say that two sets are going to be equal to each other if A is a subset of B and B is also a subset of A, then this implies that A must be equals to B. So to think about it, let's take an example. Let's say we have a set X which contains the element X such that X belongs to the set of natural numbers and X is less than or equals to 5. And then we have another set Y. Y contains the elements Y such that Y also belongs to the set of natural numbers and Y is less than 5. Now, if we try to express the set X, this is given in the set builder form, in the tabular form, then what will be the elements of the set X? Clearly, X must be a natural number and it has to be less than or equals to 5. So if we start from 1, this will be the first element. Then we have 2, we have 3, and we have 4. We'll be also considering 5 as well, because here X is less than or equals to 5. That's the symbol, less than or equals to. However, for the second case, if we consider the set Y and you list the elements using the tabular form, then the elements will be 1, 2, 3, and 4. We cannot consider the element 5 because 5 is not going to be less than 5. Okay, so that means when we are talking about numbers, we generally think in terms of the sign less than or equals to. So in parallel terms, we can think in terms of subset as this is going to be corresponding, the less than symbol will correspond to a proper subset and the less than or equals to symbol is going to correspond to a subset. So let's try to define the proper subset as well. So let's say if A, the set A is a proper, it is a proper subset of the set B. If A is a proper subset of set B, then there exists an element, let's call it X, which belongs to the second set B, such that this element X is not present in A. That's the definition. That means we can say that B, the cardinality of B is going to be greater than that of A. Or in other words, we can say that set A is not equals to the set B. Oh, the key difference between the subset A is a subset of B and A is a proper subset of B is that all the elements of A are present in B and all the elements of B are also present in A. Whereas in the case of a proper subset, all the elements of A are present in B, but there will be some elements in B which are not present in the set A. Now, we will talk about some important results that arises. Before discussing about the results, let me clarify one more thing. So whenever we are writing subsets, so here we can see that on both sides of the symbol subset, we have a set. So here a set can only be a subset of another set. It's never going to be a number that's going to be a subset of a set. Meaning, remember when we are discussing about the symbol belongs to or does not belongs to, we consider that we have an element X that belongs to some set A, or we can say if we consider number 2, let's say A has the elements 2, 4, then we can say that 2 belongs to the set A and we can say that 4 belongs to the set A. So there's a proper way of writing the symbols. So similarly, in the case of subsets, we always write a set to the left of the symbol of the subset and to the right of it we will use another set. So here if we write that the number 2, so in this case if we write the number 2 belongs to is a subset of the set A, this is an incorrect representation. We never write it. However, if we want to express that the element 2 belongs to the set A, then all we have to do is write it as the set containing a single element 2. Now this is going to be a subset of the set A. The reason behind this is because now we have represented the 2 inside a bracer, and that means that it is a set and no longer an element. Now the first result will be that every set is going to be a subset of itself. That means if we say we have a set A, we know that all the elements of set A are also going to be present in itself. So in a way, we can say that A will be equals to A, which implies that A must be a subset of A. That's a very trivial result. Let's go to the second one. The empty set is a subset of every set. Let's try to understand it. We'll try to understand it with the help of an example. Let's consider a set, a finite set with the elements A, B, and C. What we'll do, we'll remove one element from this given set A. Let's remove this element C, and this gives us a new set B containing the elements A, comma, B. We can clearly say that B is going to be a proper subset of A. That's because all the elements of B are present in the set A, but they are not equal, so we're using proper subset. Then we're going to remove another element from the set B, and this is going to give us another new set C containing the single element A. So here we can say that C is going to be a proper subset of B. C is also going to be a proper subset of the set A. Fine. And then finally, we're going to remove the element A of the set C to get a new set D, which is the null set or the void set. Now, we can easily say that the set D is also going to be a subset of the proper subset of the set C. D is going to be a proper subset of B, and D is also going to be a proper subset of A. Now, this is what we meant when we say that every empty set is going to be a subset of each set, of every set. We can also represent it symbolically as phi is a proper subset of any set A. And the final result 3 will be that the total number of subsets of a finite set containing n elements is 2 raised to the power of n. You can remember this result, or if you want, you can try to understand it with the help of an example. Let's say we have a set A that contains n number of elements. We're going to represent the elements as A1, A2, A3, and up to an. So there are a total of n elements present in the set A. Now we can pick different types of subsets from A. Now let's say if you are aware with combinations, so let's say we have n number of total elements. We can pick out 0 elements and we're still going to get a set, and this is going to be nothing but the null set. Then we can have n number of elements, and from here, let's say we pick up only one single element. So this is an example of a singleton set. It could be anyone. It could be the A1, or it could be A3, or any of the n elements that we can pick up, but it's going to be a singleton set. Then we can have 2 elements picked up from this n element set. So that's also going to be another subset of the original set A. So in this way, we can pick up all the elements from the given set, and this is still going to be another set. So that means the total number of subsets, so these are all subsets of the main set A. So that means in a way we can say that when we add them up, this is going to give us the total subsets of the original set A. So we have NC0 plus NC1 plus NC2 all the way up to NCN, and actually this is nothing but 1 plus 1. This is the binomial expansion of 1 plus 1 raised to the power of n. That will be equals to 2 raised to the power of n. So if you're not aware of binomial expansion theorem or binomial theorem, you can skip this particular portion and remember it, and once you become familiar with binomial expression, you can come back to this particular section, and then this will make more sense. So let's talk about the universal set. The idea is very simple. So whenever we discuss about a set, or when we are considering any kind of a set, it is assumed that there is a bigger set like which encompasses the universe and is usually referred to as the universal set. To understand this, let's say for an example, we have a set of all points lying on a plane. Set of all points lying on a plane. So this is going to be an universal set, which is usually denoted by the letter U. This means that we are in the domain of plane geometry. We're talking about plane geometry. So whenever we are talking about plane geometry, so this is going to encompass all the points. The universal set is going to encompass all the points lying on that particular plane. Now, once we do Venn diagram, which is going to come in a couple of sections later, then we'll be able to understand all of these types of sets in a more graphical manner. So, a set that contains all sets in a given context is going to be referred to as the universal set. Finally, we'll discuss the power set. For any given set A, the collection or family of all the subsets of A is going to be referred to as the power set of A, and it's denoted by P of A. Okay, let's try to understand it with the help of a simple example. We'll consider a set A containing three elements A, B, and C. Now, we have already discussed that how many total subsets of A are possible. So that's given by 2 raised to the power of n. Now, in our case, n will be equals to 3. There are three elements A, B, and C, which means that 2 raised to the power of 3, that will be equals to 8. So there are a total of 8 subsets possible. So let's try to write down all the subsets of A. So here, we'll start with the null set phi, because phi is always going to be a subset of the set A. We have already talked about it. Then we're going to consider the set containing only one single element, or a singleton set. That means we'll consider the first set containing only the element A. Other possibility could be set containing only the element B, or the set containing only the element C. Then we can have a set that contains two elements, that will be either A comma B, or it could be A comma C, or it could be B comma C. Or finally, we could have the main set that contains all the three elements A, B, and C. So here we can easily count 1, 2, 3, 4, 5, 6, 7, 8. So that means we have a total of 8 subsets of A. Now let's say we consider all these 8 subsets of A and then included within the braces, then this is going to be referred to as the power set of A. So it can be also thought of as the set of all sets of A. Our power set can never be non-empty. Why do you think it's never a non-empty set? Because let's say we have a set B, which is the null set phi. Now, it's going to have at least one subset, because here clearly n equals to 0, because there are no elements present in a null set, which means that the total number of subsets that are possible will be 2 raised to the power of 0 equals to 1. So that is at least one set, and that is nothing but the null set, which means that the power set of B is going to be containing at least one set, and that's nothing but the null set phi, which means it's never going to be empty, non-empty. So this brings us to the conclusion of today's lecture. We have discussed the concept of a subset and a proper subset. We have also discussed about the universal set and the power set.